Alright, so for this video we're going to take a look at parallelograms and some of the special properties of parallelograms. So let's go ahead and jump right in. First, let's just make sure we're clear on what a parallelogram is. By definition, a parallelogram is a quadrilateral, so four-sided shape, with two pairs of parallel sides. So example we see here, we have a quadrilateral where segment WX and segment YZ are parallel. Let's go ahead and mark those parallel. Those are parallel, as well as segment XY and WZ. So that's a parallelogram because it has two pairs of parallel sides. Now the first theorem that we're going to look, the first special property we're going to learn about says that when a quadrilateral is a parallelogram, its opposite sides are congruent. We know by definition that these opposite sides are parallel, but now we see that they are congruent. And I want to take a minute to explain how we would know that segment XY and segment WZ, for instance, would have to be congruent, and then the same thing for segment XW and YZ. So I'm going to kind of explain how we know that has to be true. And in order to do that, I'm going to add in a diagonal for my parallelogram XYZW. I added this diagonal in here, and that created two triangles. Now I think we can prove that these two triangles are congruent, and if they're congruent, then we would know that all their corresponding parts are congruent, which would mean that XY and WZ are congruent, and it would mean that XW and YZ are congruent. It would kind of prove this idea here. And the way we're going to show that these are congruent is we're first going to name, we're going to say that segment XZ is congruent to itself, right? And that is a pair of sides between our two triangles. And it's congruent to itself because everything is congruent to itself. So I'm going to go ahead and mark that congruent on my picture. And then the next two things I'm going to show are congruent in terms of the parts of these triangles are a couple of angles. And these angles are going to be congruent because of an idea we learned about a while back when we have parallel lines and a transversal going between them. So just to kind of highlight and show you what I'm going to be concentrating on, I'm looking at segment XY, segment WZ, and then this parallel line, or this transversal line XZ. When we have this kind of arrangement here of our parallel lines and our transversal, we learned that the alternate interior angles would be congruent. So angle YXZ would be congruent to angle WZX because they're alternate interior angles. But then we could also kind of apply the same idea to, let me kind of highlight in another color. We could kind of look at, we can look at segment XW and segment YZ, and then again our transversal here, and we can see that angle WXZ would be congruent to angle YZX. Angle WXZ would be congruent to angle YZX, which is another pair of angles. And now what we would have for these two triangles is angle side angle congruence. All right, so we can say therefore triangle WXZ is congruent to triangle YZX by angle side angle. And if those two triangles are congruent, then like we said, it would mean that their other parts would be congruent, such as segment XY congruent to segment WZ, and segment XW and segment YZ. So we've kind of proven that when a quadrilateral is a parallelogram, its opposite sides, not only would the opposite sides be parallel, but those opposite sides would also be congruent. Now the next special property of parallelograms that we're going to investigate also plays off of the idea of parallel lines crossed by a transversal. It says that if a quadrilateral is a parallelogram, then its consecutive angles are supplementary. What we mean by consecutive angles would be, as we're moving around our shape, angles that would come one after the other would be consecutive. So for instance, angle A and B would be consecutive, B and C would be consecutive, angle C and angle D would be consecutive, and angle D and angle A would be consecutive. And so what this is telling us is that if I pick any two of those consecutive angles, A and B, B and C, C and D, A and D, they would always add up to 180. They'd be supplementary. And the reason we know this is because, again, we would look at segment BC, for instance, and segment AD, and then we would look at segment CD as a transversal. Now, these two segments are parallel. Angle C and angle D form same side interior angles. And we learned that when we have two parallel lines and a transversal, those same side interior angles are always supplementary. And then we can kind of work the same reasoning going around, looking at, for instance, angle A and D are same side interiors for my two yellow lines in this transversal. B and A are same side interior angles with the green parallel lines in this transversal. And B and C are same side interiors for the two parallel yellow lines and then this transversal. So that's kind of the proof of why the consecutive angles of a parallelogram will always be supplementary. So that takes us to our next theorem about parallelograms. And this one says that the opposite angles will be congruent. And the proof for how we know this is going to be true is actually going to be pretty much the same idea that we did when we were proving that the opposite sides are going to be congruent. We're going to draw a diagonal in here, and then we're going to go ahead and say, well, we know that this is congruent to itself. We know that this angle and this angle are alternate interior angles, so they're congruent to each other. We know that this angle and this angle are alternate interior angles, so they're congruent to each other. So that means that we have a couple of congruent triangles by ASA, and then this part of this triangle would correspond to this part of the other triangle, so we'd have to say that they're congruent. So that makes A congruent to C. To prove that B is congruent to D, we would just have to basically do the same thing, except for not using this diagonal here. Let me go ahead and erase that diagonal. Instead, we would put our diagonal connecting A to C. And then we'd say, all right, that's congruent to itself. This angle is congruent to that angle. This angle is congruent to that angle. Again, our triangles are congruent by ASA, and angle B and angle D now have to be congruent because they're corresponding parts of those two congruent triangles. So that's a real quick idea of the proof behind the fact that for parallelograms, opposite angles will always be congruent. Now, lastly, we have a theorem that says that the diagonals of a parallelogram will bisect each other, which means that this diagonal would cut segment XZ into two equal parts, and segment XZ would cut segment WY into two equal parts. So let me show you how we know that that's going to be true. Again, we're going to use congruent triangles, and we're going to use the idea of alternate interior angles. Let's look at triangle XAW and triangle YAZ. I'm going to show you how I know that those are congruent. I know that these two angles are congruent because they're vertical angles, and then I know that this angle and this angle are congruent because they are alternate interior angles, that same reason we've been talking about. Then we proved in a previous theorem that segment XW and segment YZ have to be congruent. So that makes these two triangles congruent by angle, angle, side. Two angles and a non-included side. So now if these two triangles are congruent by angle, angle, side, we can say that this part would be congruent to this part. So that shows that segment XZ has been bisected, cut into two equal parts. But also this part would be congruent to this one, showing us that segment YW has also been bisected, cut into two equal parts. So again, we can prove that just because we know that this is a parallelogram, we would be able to say that these diagonals are bisecting each other, making segment AW and segment AY congruent, and segment AX and AZ congruent.